Hi guys, we're going to the next topic on graphs, and this is kind of an important topic. It's very common to have this kind of problems in mathematics. That is the notion of an isomorphism. So you might have come across it before, but it has these two roots, and iso means the same, and morph or morphe or whatever, it's a Greek word, means shape. And so this means an isomorphism or isomorphic. Isomorphism, we'll talk about what this is, but isomorphic, the adjective, means that they have the same shape. What does it mean? Well, we have already noted, I already said that if this is a graph, IBC, let's take a very simple graph, like a triangle graph, then it doesn't matter where you put. This is the same graph, I said, right? If you put it this way, and here you put A here, B there, and C there, this is the same graph because they have the same vertices and the same edges. Good, great. That's the idea, that location of the actual picture, the actual location of the nodes and the connections of these nodes do not matter. But what about this one? Now let me draw another one. If I take, let's take the same triangle, but this time I'm giving it different names, the nodes. So now, is this the same? Well, technically no, because there are now vertices with different names. As a set, they are different, right? The vertex set here is A, B, C, and here the vertex set is X, Y, Z. They are different sets. So and the same for the edges. However, they look the same, so they should be the same. And so that's the notion of an isomorphism. And that's what we're going to talk about. But in order to discuss this properly, I'm going to start with some more general stuff about graphs, how to represent graphs. So remember, the whole goal is to show that, set it up so that we can show that this is the same as that in a way that we can ignore the fact that they are different names. But other than that, they are the same. That's the whole goal. Okay, but first we start with the representing graphs, and the first thing I want to do is the adjacency list. Adjacency list. So what is an adjacency list? We have a graph. Let's make a bit more interesting graph, a little bit more connections here. Let's put this there. A, B, C, D, E, F, and let's connect these two together. All right, and suppose this is our graph. So what is an adjacency list is basically, we have already seen this. This is the neighborhoods. We just, for each vertex A, B, C, D, E, F, we list its neighbors. Okay, so for A, we have the neighbors are, you see, B, F, and C, so we just list them. Now, in which order you say, doesn't matter, because remember, order doesn't matter here. So these are the neighbors, and this is the neighborhood set. So we have seen this kind of table already, but now we have seen the official name of it. And then let's do this for each of those, A, B, C, D, E, F. So for B connects to A and F. You're very careful when you copy this data, because this is, once you have this graph, once you have made the table, you're going to reason with the table or with the list rather than with the graph. The graph is a representation, a visual representation, but it's hard to work with. So we have to distill information from it, and that is the adjacency list is one. So let C is A and D, so, and then D connects to C, D and, no, not D. Well, D cannot connect to D because it's a simple graph. So C connects to, where am I? D connects to C. E and F. E only connects to D, and F connects to B, A, D. Yeah, B, A, D. Now, immediately, of course, we can calculate the degrees. That's just the number of elements in the neighborhood set. So 3, 2, 2, 3, 1, 3. And we can always, there are what we call, I call them sanity checks, ways of checking that the data you have copied is correct. One thing we know is that the number of odd degrees has to be an even number. So just 1, 2, 3, 4 odd degrees, so that works out. If that's wrong, then you forgot something. Okay, but you should be, it's good to double check that your table is really the graph, because if you, from now on, we start working with this, and so if that's not the same, then yeah, you're talking about a different graph. Okay, so that's what we call the adjacency list. And you can do this for a graph, or you can do this for a directed graph. So I'm gonna do the same thing now, but I'm gonna put arrows on my graph. So I'm gonna erase this again. So let's see what happens if I do this with the directed graph. So now we have, like, say, arrows here. Sorry, there's an arrow here. We can make an arrow go back. That's allowed now with indirected graphs. So we have an arrow here. Let's make an arrow this way. Let's get this arrow this way and this way. An arrow that way. And an arrow here, perhaps. Okay, let's do it that way. Now, we know that in directed graph, the order is a little bit different, right? So we have an initial. So this will be the initial vertex, and this will be the terminal vertices. So that's important to, but it, of course, it's still the neighbors, right? It's still, if you start from A, but now we look, what is a neighbor here for A? B is a neighbor because you go from A to B. But what about F? There is a connection, sorry, there is a connection between them, but it is in the opposite direction. So A does not go to, A is not an initial vertex in this arrow, so we should not mention it. So we have only A and C. B and C. That's for A. Now let's do the rest for B. For B goes to A, B goes to F, and that's it, right? C, where is C? C goes to, okay, I'm gonna make little changes here. I wanna show you something so let me do this, the arrow in the other way. Okay, but C. So C goes to D. So C connects to D, and that's the only one, right? Yeah, okay. D connects to C. D connects to E, and D, no, not to F, because that goes the other way. And then E. Look, although E is connected, there's nothing going out of E, so E, there's nothing there. So it can be that this is an empty part here, right, in the adjacency list. And then finally F goes to B and goes to A. So what is now the number of vertices that we have here? That is the out degree, which we call degree plus, right? So this is 2, 2, 1, 2, 0, 2. Now you say, oh, professor, wait, we have one odd number. Can that be? Yes. When you're dealing with directed graphs, the degrees can be odd, or even there's no restriction there. So if you were, this adjacency list in the directed graphs gives you the out degrees, but if you have to calculate the in degrees, you have to do that separately then. Okay, so the table doesn't let you immediately read off the in degrees, but okay, we're mostly going to work with simple graphs, with non-directed graphs, so so that is a bit of less of a concern here. So that is one way, I presented the graph, but that's not the only way, and I'll talk about why there are different ways and what the advantages of this. Another way of doing this, yeah, I'll draw a new graph here. Let's make a new graph. I'll do it a little bit smaller this time because you'll see why. Let's say these are connected. Like do this. So A, B, C, D, and E. So instead of making the adjacency list, I'm going to make what is called the adjacency matrix. Adjacency matrix. So what is that? Well, a matrix is just a fancy word for a table of numbers, and this will be a binary. So this will either be ones or zeros, and it's always going to be what it's called a square matrix. This has the same number of columns as rows. So a matrix normally has no lines in it, but for me to write it, I'm going to divide it here in 5 columns. 1, 2. Well, let me do it a bit nicer. Okay. A matrix, okay, so we have A, B, C, D, E, that are going to be the labels of my column, but it's also going to be in the same order, and that's important. And remember, the order in which I list them is not important, but once I decide on an order, I have to stick with it. So I have to also write them in the same order, and I'm just using the alphabetic order here, as a columns. They are the labels of a column. So the matrix is actually the part in here. This is what the matrix will look like. We normally put some brackets like that around it. And so what goes in here? So in each of these squares comes either, it's a binary, so either 1 or 0. 0 means no edge, 1 means there is an edge. Okay, so let's do this. For A, well, there's no edge from A to itself because we don't allow loops in simple graphs. There's an edge from A to B, so we have a 1 here. There's one from A to D, a 1 here, but nothing to C and nothing to E. Okay? Again, I I prefer to do first, see what's in there and then make the rest 0, but you can also just go through the list. And now keep doing this. For B, what connects to B? Well, A connects to it. Does B connect to it? No. Does C connect to it? Where is C? Yes. Does D connect to it? No. So that's a 0, because E, yes. Okay, down with C, here is C. C only connects to B, so this is going to be the only one here, and all the rest is going to be zeros. Easier if I do it that way. What about D? Connects to A and E, so to A and E, and the rest is zeros. So it's sometimes easier to just put the zeros. Normally there are less edges than there are non-edges, right? Although that's not necessarily the case. Remember, a complete graph, there everything is edges. So, okay, from D to E, there's a no, that's not D to E. From D, so from E to D, okay, and then also from E to B, and the rest is zeros. Okay, so notice a couple of things. First of all, since there are no loops, this all has to be zeros, right? Because this would be a loop if there would be something here. You can use, by the way, adjacency matrix for non-simple graphs and even for directed graphs, but let's just stick to the thing that we will talk about most. Another thing to observe is, look at, there's a symmetry here, and the symmetry is actually, again, along this axis. If you flip this matrix, so if you flip it this way, or then therefore it flips over, you get exactly the same matrix. And that is no surprise, right? Because if you have a 1 here that says that there's an edge between C and B, there should also be a 1 here, because that's the same edge. So you see here, this is the mirror image of this. So think of this as a mirror, and then this part is mirrored in this part. This is what we call, if for those that have taken linear algebra, this is called a symmetric matrix. Symmetric matrix. Okay, there's again a sanity check. If this is not symmetric, you forgot something. What else can you read of this matrix? Again, the degrees are easy to read off, right? The degrees is the number of edges, and here we denote what's the number of ones. So you just sum up each of the rows. You just take the sum of the rows, or the number of ones. That is 2 here. So here there would be 3. There's 1. There's 2 and 2. Sanity check. 1 odd, 2 odd. That fact checks out. Okay. So this is called an adjacency matrix. There's a reason that adjacency matrices can be used, and one of them is we will use soon. We will use both of these things when we talk about graph isomorphisms. Remember, this is our original goal. As I said, you can do this for multigraphs, and then what happens then if you have, say, let's do one multigraph. I'll do it in a different color. I'll do it in red. So suppose we had this edge also twice, so that would mean I would have to write a 2 here. And of course here also 2, it still has to be symmetric. There could be a loop, and if there is a loop, well, then I would have a 1 here. Okay, but that's the only differences. It is still symmetric. You can still calculate the degrees. Of course, now that this degree would have become 3, this is now 4, this now is 2, and these 2 have not changed. Is that true? Yes. No, right. Because why was I hesitant? There's only one odd degree. Remember, this is true for any graph. It doesn't have to be a simple graph. So this cannot be. What mistake did I make? There's a loop, and a loop has to be counted twice. So you had a 1 here, and I added 1, but the loop, because you see, you have it comes in once here, and it connects there twice. So this contributes twice here. So that's a bit a weird thing. So when you have non-simple graphs, you have to be very careful what you do with the diagonal. Oh, I put my diagonal on the wrong spot. Where's my... No, it's... I'm sorry. I put it wrong. I'm sorry, guys. This is not where it goes, right? Yeah. No, I made a mistake here. So this is where the one... This is the new one. This here. It was... I broke my symmetry because I was looking in the wrong column. This is now a 1 because there's a 1 loop from D to D. But it has to be counted, so this was still 1, this hasn't changed. This has to be counted twice, so this becomes now 4. I'm sorry, guys, I put this in the wrong spot. So I told you have to be very careful with these things. Okay, now you see it's back symmetric, so everything is as it's supposed to be. And also we have now 1 odd degree, 2 odd degrees. So everything is working out again. Now for directed graphs, there is, of course, let me do a very, very simple example because I don't want to spend too much time on it. To do black again. So if it's a directed graph, things are again different because, say, let's do just with 3. We have a arrow there, and let's put an arrow back here. So we have now A, this is A, this is B, and this is C, and so A, B, and C. Okay, so again, nothing, there are no loops, so I know already these are going to be 0. Now let's think about it. There's an arrow from A to B, so from this is supposed to be this part is the start, initial, and these vertices are considered the terminal one. So I will put a 1 here if there's an, see, we go from A to B, so a 1 here because I start from A and I go to B. But there's also from B to A, so I get a 1 here. But here, let's look at this one. There's an arrow from A to C, so we will have a 1 here. Okay, let's write it there, that's a 1. But there is no arrow going this way, so this should be a 0 here. So now you see that the symmetry is broken because it's a directed graph and there's nothing else anymore. Right? Oh, I forgot to, okay, I don't know what happened here. See, this is no longer symmetric because it's a directed graph. It's only for undirected graph that you have a symmetric matrix. Okay, again, that's, we mostly will deal with simple graphs, so I don't want to say too much about the directed graphs. Next way of, there's one more way of representing, and I'll say a bit later about why there are different ways. This is called the incidence matrix. Incidence matrix. So what is a little bit annoying with the adjacency matrix is it's all about the vertices, and you don't know about the edges. So right, you know there is an edge, but sometimes you need to talk about a particular edge. You want to give a name to the edge. So let me draw my graph again that I had here, or something similar, doesn't have to be the same. So we have A, B, C, D, and E. I'm just going to draw a random graph again. Like this, and then one there, and this one there, and there. What else? Well, let's connect these two also. Remember, crossings are allowed. It doesn't mean that there's a node there, right, where I cross. That just, you have to ignore the crossings. Okay, so I can make the adjacents list of this. I'm not going to do that. But what I'm now going to do is the incidence matrix, because I'm going to label each of the edges. I'm going to give them names to kind of make them look differently than vertices. I'm going to use letters in the alphabet. I'm going to do Greek letters. So let's call this alpha, and this is beta, and this is gamma, and this is delta, and this is epsilon, and this is omega. By the way, I'm sitting here with two cats, and one is called alpha and the other called is omega. So that these things, you can give names to whatever you want, right? Okay, so how am I going to use this? Now, and there is the convention is that we're going to make a matrix again, but here we, so in there, this is going to be the vertices, where these are going to be the edges. So the edges here, let me give some space that I can write them. Okay, so this is now somehow no longer symmetric, right? So we have now A, B, C, D, and E. There's still 5 vertices, but we have more edges. Normally there are more edges than vertices, right? We see that often. Alpha, we have beta, we have gamma, we have delta, we have epsilon, delta, and then omega, right? So if I have everything now, 1, 2, 3, 4, 5, 6, right? Okay. And so, same principle. A 1, if there is a connection, in other words, remember that is called incident or adjacent. So let's look at this, what this means for A. Is A an endpoint of this vertex? Well, sorry. Is A an endpoint of this edge? Misspoke, right? Yes. So we're going to put a 1 there. Is A vertex of beta? Yes, a 1. Is A vertex of gamma, an endpoint of gamma? No. In fact, it's no longer the case, right? No for delta, no for epsilon, and no. Yes for omega. Sorry, I forgot omega. Yes. Okay. And now we can do B. Now it's more systematic if you just go through the edges that go through B. So alpha, epsilon, delta, and gamma, and so the rest is 0. Okay, let's go to C. In C, I have beta and epsilon. Beta and epsilon, so the rest is 0. D. D has delta and omega, so delta and omega. E connects only gamma, so only gamma is there, and the rest is 0. Now, I repeat, I draw these lines here so that we better see what it is, but actually it is supposed to be, this is how the matrix looks like. So, okay, I'm going to try to get rid of it. So this is how the matrix is supposed to look like. Oh, I cannot go inside because it's gonna... And then even these top guys are not there. So the matrix is just the ones and zeros in a list like that. That's how a matrix looks like. But for legibility, I like to put my things here. I already make the mistake in the last case, even with the lines. So without the lines, imagine what silly things I would be doing. Okay, what can we read from this matrix? First of all, is this a symmetric matrix? There's absolutely no... Well, for one thing, it cannot be symmetric in this case because there are different number of rows and columns. Remember, if you flip it over, it cannot be the same, because if you flip over this matrix, there is no diagonal even. What's the diagonal? That just doesn't make sense. Okay, but it is definitely not symmetric. This for no reason. It's absolute. The rows are vertices. The columns are labeled by edges. But I can still read off things. Well, the degrees, how would I read the degrees? Should I take the sum of the... Should I sum this up, or should I sum this up? Remember, in this case, we could sum these guys to get the degrees, but we could have, even for the same reason, some of these, because it's all symmetric. But that's not the case anymore, so now we have to decide. Of course, it's this way, right? Because this tells me the vertex, and this tells me exactly what its edges are. So degrees here, counted here. Sorry, 3, where I get, this is 4, this is 2, this is 2, and this is 1. Chanity check, 3, 1, okay, that's the right number. What is then this? What would this give me if I start summing up? It's always 2, obviously, because every edge has exactly 2 endpoints. We're not accepting loops, right? And I'm not going to talk about incidence graphs of more complicated things. Let's just stick to this case. So this always has to add up to 2. So in other words, that's also a sanity check. If that's not the case, then something is missing. Okay, so this is an incidence matrix that reflects the information of the graph. And so a good practice then is, if I give you, let's see what I can. Let's make an incidence matrix. I'm going to do it a little bit shorter. Let's say 3, and I have alpha, beta, gamma, and delta. Okay, suppose we have to have a 1 here, a 1 here, and a 0 there. Remember, in the columns there can be at most 2 1s. So I'm going to do a 0 here, a 1, and a 1. No, not at most, exactly 2. Sorry, I said that wrong. A 1, a 0, a 1, and a 1, 1, 0. Well, that's going to be a bit of a problem. Yeah, I took a little bit too few. Let me add a D here. And so, okay, make this then... otherwise, it's very hard to give an example that is so small that is somehow relevant. So, okay, and I'm going to make this a 1 and make this a 0. Okay, so let's represent this graph. So we have 4 vertices, A, B, C, and D, and we happen to have 4 edges, but that is just coincidence. Let's see. A is connected to alpha. So we know that alpha is going to go from A somewhere. But where? Well, that's how you now actually read this thing. So let's see. Alpha connects A into B. So that's how we now read it. So I'm going to do this in... No, I'll do it this same color. Alpha, this is alpha. What is beta? Beta connects B and C. B and C. So this is beta. What is gamma? Gamma connects A and C. A and C. Okay, that's gamma. and delta connects B and D. That's delta. So you can reconstruct the graph from the incidence matrix, as you can do it from the binary, from the adjacency matrix, as you can do it from the adjacency list. Okay, I didn't do it for all those. I hope that that was more clear. But here, this is perhaps something you might wonder a bit how to do it, and you need a little bit. You have to start. You have to look at the various edges, how they connect. Okay, because now they have names. That's the difference. There's more information. Yes or no? There's no more information because we just have given names here. But it makes it easier to talk about this graph when we talk about edges as well as vertices. Often we only need to know the vertices, but once in a while we need to also know. We have to talk about the not know, but talk about the edges, so they need to have names. Okay, so this is all that we need to talk about, not all that we're going to use, when we to discuss this problem from the beginning, isomorphism. Now, before I say something about that, what about adjacency list and adjacency matrices? Is there an advantage of both of them? I'm going to let you read that in the textbook. It explains a little bit when certain things are better than other things, but we'll see we will use both. The incidence matrix we will not use really much yet. Okay, so our original example of the two triangles. Okay, so we have A, B, and C, and we have X, Y, and Z. And our claim is this should be considered the same graph. Just because I give them different names shouldn't make it different. Right? After all, we are allowed to give names here. And so this is the notion of a renaming, or the official name is that of an isomorphism. So an isomorphism, so we have a graph G here, and the graph H, and the graph G has vertices A, B, and C. So I write V for vertex, subscript G for graph G, and here, so this is X, Y, Z. So what is an isomorphism? Isomorphism is a renaming. So I'm going to rename A, I will rename it XA, and B, Y, and C, Z. Right? So what does that mean is, it comes down that I have a map from Vg to Vh, a function, and in fact I have a bijection. Which one? So as I said, I'm going to name A X, I'm going to name B. Notice my usage of this arrow with a little head, with the head here, that is a line. When a function is denoted by an arrow, don't confuse this with by the directed graphs, right? This is just a function. So let me make it a little bit. So a function is denoted by an arrow. The elements, it maps an element A to X, B to Y, and C to Z. And it is bijection means that every element in the left has to be mapped to exactly one element in the right, and there should be nothing missing. For one thing, therefore, they have to have the same number. Right? If they're on the right would be 4 vertices, there's no way I can rename them. Right? If there would be a vertex W here, even if it's not connected to anything, I cannot rename W in with the names A, B, and C. I have used them. So that's one thing. We'll talk about that later. The number has to be the same. So that's a bijection. But of course, that's not just any bijection. I mean, it's a bijection, but there's more to it. Because, look, fine, I have this bijection, you convinced me, but what if I erase this edge? Are these two graphs isomorphic? No, they shouldn't, because for one thing, this is like everything. No, it's not, right? They don't look the same. There's no renumbering. Well, this is or renaming. This is a renaming, but what is failing here is, look, we have an edge between A and C, right? But what is the new names of A? A becomes X, C becomes Z, X and Z. They don't have the same name. So to be an isomorphism, the requirement is that if A if AB is an edge, then the image of F, let's call this now sigma. So we give a name to this. So this is a map, and so the way that we write is that sigma of A, that is X, and sigma of B should also be an edge. And no matter what sigma A and sigma B is, okay, we see here it's X and Y, but in general, we have what we're going to have. So a graph isomorphism is a bijection sigma from the vertices of the first one to the vertices of the second one, such that if A and B are vertices in G and AB is an edge in G, then the image of this edge, so it's, sorry, I have already written down sigma. Then the image of A, which is sigma A, the renaming, the new name, that's sigma A. The new name of B is this. This should also be an edge now in H. But in the original triangle, this is the case, right? So let me make my triangle back as it was. Now this fits this definition here. So you see, it's kind of a little bit of work to check that, right? I can give this. This is very easy. These three vertices here. But if the number of vertices, let's look at this one here. Again, we have to have the same number of vertices. So this is A, this is B, this is C, and this is D. And let's make just a square. This was C4, right? Okay, but now I'm going to mess up C4. I'm going to write it this way. So this is X, Y, X, Y, Z, and T. I'm doing this. You might say, why are you going this way? I have a reason. Because when I start making a graph, it doesn't matter what names I give, right? So I've decided I give these names to this guy and these names to these guys, okay? So what is now a renaming here? Okay, so you say, okay, name A X, name B Y, name C Z, and name D T. That's not really alphabetical, but I think this is okay. Well, let's see, is this okay? I have an edge, so this is sigma. Is this a graph isomorphism? It is a bijection between the vertices of the left, so let's call this G, and this is H. So here is V, and here is H, right? So it is a map, sigma. So it is a bijection. Remember, a bijection means that it is injective and surjective, or another way of saying that it's reversible, right? It has an inverse, so I can A corresponds to X and vice versa. X corresponds to A, and very often we think of this in either way. We don't really consider it in a particular direction. It doesn't matter which way we go. Is this a graph isomorphism? It is a bijection, but what is missing is, look, we have the edge AB. That's an edge in G. I haven't named it, but I can always, every edge can be denoted just by listing its endpoints. So what is sigma A and sigma B? Is this therefore this should now be an edge in H. Well, sigma A is X, sigma B is Y. Oh dear, that's not the case. So they are not isomorphic, Professor. I'm convinced. Well, perhaps you took the wrong renaming. I mean, these graphs are not. Why? What was the mistake here that I made? Let's look a little bit at. No, I cannot say it that way. Yes, let's look at the difference. So this is not, but I'm going to propose another one. So what about I'm going to call it tau, which is a different. Oh, so this is from. Sorry, I don't know why I wrote V here. It should have been G, right? From G to H. So this is another Greek letter, tau. And I'm going to send A to X, or that I'm okay with. But B I'm going to send to Z, and C I'm going to send to T, And then D, where can I send D to? Well, now I have no choice anymore. It has to be Y, right? Everything has to be on the left and right, they have to correspond to each other. Is this okay? Well, let's see. What happens, I'm going to do it with colors. AB, okay? That edge. Well, A is sent to X, so I'm going to do this with arrows now. A is going to X. Now, okay, I'll do this in different color. What I'm now drawing, my arrows that I'm going to draw, let me do it in purple, are the maps, the renaming. So perhaps I should make it dotted like that. It's not part of the graph. So A goes to X. And then B goes to Z. So I repeat, these arrows that I'm drawing now, it doesn't make it, it's not graph arrows. This is just another visual representation of my renaming. C goes to T, and D goes to Y. So let's see what happens to my edge, my green edge here, this one, A to B. A went to X and B went to Z. So, oh, it's this edge. So when moving these two, A and B, to X and Z, I also moved the edge. That's what I want. Okay, what about the other edge? So let's do all different colors here. This edge, from B to D. Now, B is, be careful now, we are dealing with this, with the bottom one, right? B is sent to Z, so we go from Z here. I'm going to start there. And then I have to go D. So the original one goes from B to D, and D, so let's say, this is the edge. B goes to Z, that's Z, and D goes to Y, so that is Y. So my new edge, if you want, should be this, and that's indeed the edge that is already there. So this edge corresponds to another edge that's there. And you can keep going very quickly. C and D. C goes to T and D goes to Y. C goes to T and D goes to Y. So this T and Y, that's in the blue edge, blue. And then finally do, let's one more, do red. From A to C. That would be what edge? A goes to X and C goes to T. So that would be this edge. So that's how you can think of it, right? So we have not only that we move the vertices or rename the vertices, but accordingly the edges are moved as well. And that is when we have a graph isomorphism. Okay, this is very simple examples. We'll do a little bit more complicated examples later. But now comes the problem. How do we know that a graph is isomorphic? What does that mean? Well, these graphs have to be the same. Right? That's the whole idea. Remember, the original meaning of the word, the etymology of the word is same shape. Okay? So, although visually they look different, right? But we're now convinced they are the same shape. It's just that we have, if we untangle it, you can think of it like, it's like a knot, the same thing, right? If you untangle it, it comes down to the same picture that you have. Yeah. Okay. So this is a notion of a graph invariant. What is that? That is a property that is preserved under isomorphism. Now this looks like a very complicated sentence, and so I'm going to try to tell you a little bit in more down to earth terms. It means the following: a graph invariant is an information on the graph G, and you have so it could be, for instance, give me an example, the number of vertices. So the number of vertices of G. Oh, I see. This is VG and this is VH, right? So that's why, okay. And the number of vertices of VH. The number of vertices are the same because we have a bijection between the two. In my definition, where is my definition here? I have a bijection, which means that I have to have same elements here, the same number of elements here as the elements here. So that's a graph invariant. Not the sets themselves. They are not invariant because I can map one set to another set. That's not invariant, but the number is invariant. That is because it is a property that is preserved under isomorphism. There are 4 edges here, therefore there are 4 edges there in this particular example. So that's what a graph isomorphism, a graph invariant is. There are 2 things it's a information that a graph invariant is information that you distill from a graph that does not depend on what particular representation of the graph you have. It doesn't matter whether you take the graph or you take a graph after an isomorphism, because they are supposed to have the same shape, therefore they have the same graph invariant. What else is a graph invariant? Well, let's look at, for instance, let's look at an example that we have. Well, I haven't gotten any straight examples yet, right? So, sorry, no, let me go here. Okay, I'm going to make another one. So here's another one. So I claim that these two graphs are I claim that these two graphs are isomorphic. Now I don't even have given names to it. So A, B, C, and D. No, not A, X, Y, Z, and T. Yeah, by the way, if you want to really get confused, I can give these also names A, B, C, and D. They are different than these. I don't know. I don't like to do that, but sometimes people do that. So, okay, so what is an isomorphism here? I'm going to write down isomorphism. I'm going to map A. What do you think that A goes to? Any guess? Well, A has to go to Y. And I will explain later why this is what I have to do. Now, what I do with the next actually doesn't really matter that much. So here is an example. So this is my sigma here. Let's see why I'm doing this. Let's make the adjacency list here. Because as I told you, these things are going to come up, right? So here we have A, B, C, and D. Now, A has vertices B, C, and D. B has vertex A. Neighbor, sorry, misspoke. And therefore we can calculate the degrees. There's 3, 1, 1, 1, 4 degrees of odd degree. So that's good. And now, okay, what is an invariant here? Let's think about. If I'm going to send A to one of the vertices here, then what has to happen is, we've seen this, when you make this map, edges are moved around as well. Now, A has 3 edges, so these 3 edges have to be moved around, and they all have to start from, if I send A to X, then they all have to start from X, these 3 edges these 3 edges would be moved. If I move A to X, then these 3 edges should be 3 edges that come out of X. That's not possible because X has only 1 edge. In other words, what I'm trying to say here is an invariant of a graph invariant is degree. So let's lose a couple of the degrees. In particular, the number of degrees that we have. So let's make it quickly here. So this was VG and here's VH. The adjacency list for H, that would be X, Y, Z, and T. This would neighbor Y, Y, and Y. And here this is the one with the many neighbors, 1, 3, 1, 1. Notice that we have 1 of degree 3, 3 of degree 1. 1 of degree 3, 3 of degree 1. Not in the same order, because after all, that's what an isomorphism does. It jumbles up, it renames things, right? But that's important. So when I say degrees is a graph invariant, what I mean is the number of edges of a particular degree have to be the same. But not only that, an isomorphism has to preserve the degrees. In other words, if I want to send A to one of these guys, the only choice I have is to send it to the one of degree 3. Now, in this case, I have only one choice, so A has to go to Y. That's what I was saying. I have no choice here. If there's an isomorphism, that's what it has to be. A has to go up to 3 because the isomorphism has to preserve the degrees. What about B? Well, B has degree 1, so B has to be sent to one of these guys of degree 1. Which one? Sometimes it matters, sometimes it doesn't. In this particular case, it doesn't matter. So what I wrote down here is actually a graph isomorphism. It's not so hard to check, so I'm going to leave that to you. But I want to give some more complicated examples where it's no longer obvious that we have isomorphism or not. So here's an example. Let's make like a little houses like this. Sorry, my drawing is not always very pretty. yeah, this, I shouldn't do this, right? That should be a nice connection. And let's connect it this way. So this is A, B, C, D, and E. And then I make another guy like that, at same configuration. Let's call them X, Y, Z, T, and U. And we have a little roof like that. And then we have this and that and that. Okay. The number of vertices in both cases are 5. So let's look. So here are the graph invariants. Let's list them here. Yeah, let me perhaps write them here. I'm going to do it this way. Sorry. And graph invariance. So the first one is the first one I could consider is the number of vertices. So this is my G here, and this is H. So how many vertices I have? 5 here, and I have 5 there. Okay, so this I'm making like a table and verify everything. Now what about the degrees? I can make an incidence graph, but I can also just mark the degrees on the graph, right? Let's do that. That's quicker. A 2 here, 2, 1, 2, 3, 1, 2, 3, 3, and 2. Okay, and here we get a 2, 1, 2, 3, 4, 1, 2, 3, 2, and 1. Okay, so what are the degrees here? So how many are there of degree 1, degree 2, degree 3, degree 4? That's all that happens, right? Let's see. Let's mark the number of them. In the first one, there's nothing of degree 1, but there is 1 in the H. Degree 2, we have 1, 2, 3, and in there we have only 2. In degree 3, we have 2 in the left. So this is the number, right? And here writing the number of, I hope that is clear here. What I'm writing down is the the number that, sorry, I will do that. The number of vertices of each degree. And degree 4, there's none here, 0. So what is here? Degree 3, I have 1 of degree 3, and I have 1 of degree 4. Okay. Be careful. How about the odd degrees? Well, these are the odd degrees, right? 1 and 3, so there's 2 of them here, and 1 and 3 is 1 and 1, so 2 again. Everything is correct. But you see, they don't match. So this means this cannot be isomorphic. One way of thinking that is, okay, I have no degree 1s. So, and here I have 1 of degree 1. So if I, whatever, remember there has to be a correspondence in either way, right? It doesn't matter where I go from G to H or H to G. It goes both ways. T, where am I going to send T to? Whatever choice I make, the problem is that any choice has at least 2 edges, whereas this edge will be moved in one way or the other, but that's the only edge that will ever come from come from here. So that's why there is no isomorphism. So they are not isomorphic. Oops. Not isomorphic. Now that's quickly seen, but unfortunately, it's not that easy, and I will say more about that here. Let's look at these graphs here. Let's say we have so we have 2 squares, or 2 rectangles rather, sitting inside each other. So there are 8 edges in both, so that's definitely the same number. Not going to even mention that anymore. And we have also furthermore, this is connected there, this is connected there, this is connected there, and this is connected there. So this is A, B, C, D, E, F, G, H. I'm just making the choices like that. Now we have a lot of vertices, so I'm going to start with S, T, U, V, X, Y, and W, Z. I don't know why I did it that way. It's not really alphabetic. Okay, it doesn't matter, right? So let's look at the degrees here. Again, I'm going to write them for simplicity up here. That is degree 2, degree 3, degree 3, degree 2, degree 3, degree 2, degree 2, degree 3, and degree 2. Here I have degree 3, degree 3, degree 2, degree 2, degree 3, degree 3, degree 2, degree 2. I hope by now that you're convinced that just looking at the fact that they look different doesn't mean anything, right? We have seen, okay, so far I actually haven't seen really very complicated examples, I guess, yeah. So you can still say, oh, they look different, so they are different. No, I should, you should be careful with that. Okay. So, let's see, how many of degree 2? So I'm just counting, here's the number, the number of them, right? Degree 2. We have 1, 2, 3, 4 of degree 2, and here we have 1, 2, 3, 4. Degree 3, we have 1, 2, 3, 1, 2, 3, 4. And here we have 1, 2, 3, 4. Okay, that's because that's the only degrees that are possible, and there have to be 8. So they match. So they are isomorphic? No. No. That not necessarily mean. What it does mean is if you have an isomorphism, anything that has degree 2, any of these guys that has if this one, where should I map it to? There are only 4 possibilities. I have to map it either to this degree 2, this degree 2, this degree 2, or this degree 2. I cannot map a degree 2 to a degree 3. That's the idea of degree is a graph invariant. So I have 4 choices for this guy. Okay. But will it work or not? So now I need to look, and this is why I first introduced these adjacency list. Let's make the adjacency list. That's a bit of work, and so I'm not going to make the full adjacency list. Let's make the adjacency list of here, of A here. So, okay, so, no, sorry, that's what I was saying. Here, let me make the list here. So, here are my vertices, here are my neighborhoods. So, let's look at A. A has neighbors B and G. Okay. So, that's a degree 2 vertex. Let's look at all the degree 2 vertices. So this is VG. Let's all the degree vertices over here that I have. Sorry, I'm making my matrix. I hope you can still follow a little bit. There's a big dividing line here. This is a divide line, right? This is just the line between the two. Okay, so so here is going to be the neighbors of these guys. So what are the degree 2 here? We said that was X, Y, W, and Z. Okay. Bear with me why I'm doing this. So what are the neighbors of X? The neighbors of X are U and Y. U and Y. The neighbors of Y are X and V. X and V. The neighbors of W are S and Z. Of course there has to be 2 because I picked the degree 2 ones. Z is W and T. I have not made a full table because I don't want to waste too much time here. Okay. So, okay, professor, so what? Okay, so what this means is if A has to be sent to one of these. But it also means that if I send A to one of these, say I send A to X, then B and G have to be sent to U and Y. Now, which way, that we don't know yet, but it's sure that, for sure, because neighborhoods are degree invariants, so graph invariants. So where I'm listing my graph invariance degrees, sorry, I went myself with space here. Neighborhoods are graph invariants for the same reason, right? Because we not only mapping a point, we mapping the edges of the point at the same time, right? This point is mapped to here. No, to where does this point go? Sorry, this point C is mapped to T, but its 2 edges are mapped to T2's edges because A is mapped to X. Yes, A is mapped to X and D is mapped to Y. Okay, so that's why not only vertices are preserved, but also these edges, and therefore the neighborhoods are preserved. Okay, going back to my table here. So, what I'm trying to say is, wherever I send A, I know that, for instance, I send A to X, then B and G must be U or Y. So B must be U, or G must be Y, or vice versa. That I don't know yet, but that's the only possibilities. Okay, and now I'm going to do a next thing. We know the degrees. Okay, let me just for completeness write the degree here. So this is both of degree. They are all both degree 2. There's more here, right? And there's more here, but trust me that we don't need that. What I'm not going to write is something, there's no good notation for it, so I'm going to vent a little bit. I'm going to say the degree of the neighborhoods. So I'm going to list the degrees of all the elements, vertices in the neighborhood. So in other words, what's the degree of B? The degree of B is 3. What's the degree of G? It's also 3. You saw that? Yeah, so B has degree 3 and G has degree 3. Okay, so 3, 3. So it's a list that I get that is its combo of degrees. And since neighborhoods are graph invariants and degrees of invariance, this is a graph invariant, the list of numbers that I get here. Now let's look what happens here with the degrees of the neighborhoods. What is the degree of this neighbor, U? That has degree 3, okay, so 3. What is the degree of the neighbor Y? That's degree 2. Oh, that's not the same. And we said that what pattern that I get here, except for the order is not important because we don't know whether B goes to U or B goes to Y, or G goes to U and G goes to Y. This goes to one of those, and this goes to the other. But how do we know? We don't know. But this has to match. 3 can go to 3, but then this one says, hey, I need something from degree 3 and you don't give me anything anymore. So therefore we know that A cannot go to X because it would not, these two things are different. Okay, so we have to look further in the list and then find where it would match. So X, what's the degrees of X? That's 2. And V is degree 3. I'm saying because I have a degree 2 again, and that's not supposed to happen. Okay, forget about, so W is going to be the savior, because W, this guy has degree 3. See, I told you it's going to be the savior, and the other neighbor Z is going to be has degree, it has degree 2. Oops. And if you very quickly see, W has degree 2 and T has degree 3. So I repeat, I'm now writing down the degrees of these neighbors, right? That's these numbers correspond to. Now, the 2, 3 and 3, 2 are considered the same because the order doesn't matter. But the difference is that we have 3, 3 here and that we never have that pattern here. And that's why they are not isomorphic. So, not isomorphic because this graph invariant does not occur here. It cannot occur in the 4 other ones because they have degree 4. That one is not going to work. Okay? So, is that then the end of the story? Well, the problem is that even it can be that these things match and still they are not isomorphic. Now, these are already very complicated things, and I don't think we will run into this. So, if it's not isomorphic, you're going to be able to find it out one way, like through looking at the neighbors. So we have to dig kind of deep before we can see what's not working. But at the same time, and this is the problem of graph isomorphism. If I give you 2 graphs, you kind of don't know in the beginning what's going on. So I'm going to copy 2 graphs here. It's going to take me a little while because they're also kind of big. Well, big, no, it's not that big. Okay, so here we have this one. So A, B, C, D, E, and F. The book uses numberings. I kind of find that very hard to follow with numbers, and so I like to give just better numbers here. And then I have also this guy. No, this is not what I want to do, sorry. This guy. I think I copied it right. I hope I copied it right. Okay, so let's give them names. S, T, U, V, W, and X. Okay. 6 on both sides, so that doesn't exclude there to be a graph isomorphism. So we have to go dig deeper. Let's look at degrees. And again, I'm gonna, for simplicity, mark them here. This has degree 2, this has degree 3, 2, 2, 3, and 2. This has degree 3, 2, 2, 2, 3, and 2. So I see there are degree 2, there are 4 here, and there are also 4 there, and degree 3, there are 2 here and also 2 there. So that matches. But in particular, it also tells me that if I'm going to send E, I cannot send it to X because that has degree 3 and E has degree 2. So it narrowed down a little bit the possibilities. Now let's look at, so this doesn't exclude anything. Hopefully the next one will, namely, now I have to make the neighborhood lists, right? The adjacency list, and then look at the neighborhoods, and then hopefully from there I can figure out that something is wrong. So I'll do this. Oh yeah, I'll go all the way like that. It's not. No, I shouldn't do that, but okay, I did it. So remember, there's still a dividing line here between the two, right? They have nothing. Okay, keep. So here we have, that's the vertices, the neighborhoods. The neighbors of A are B and C. This is neighbors. Okay. The neighbors of B are A, F, and D. A, F, and D. The neighbors of C are A, E, and D. A, E, and D. D has neighbors B and C. E has neighbors C and F. And F has neighbors E and B. Right? So the degrees. I'm sorry. I'm gonna sneeze again. Don't. So the degrees 2, 3, 3, 2, 2, 2. What we already found. Here, so this is V of G. I'm sorry, guys. I sometimes get these sneezing bouts. Don't worry, it's not COVID. Remember, I said I had 2 cats, Alpha and Omega. They're not my cats. They're my sister-in-law, her cats, and I'm allergic to cats, so that's why I'm sneezing. But they're nice. I like them. Okay, so the S, T, U, V, W, and X. So what are the neighbors? The neighbors of S are W, V, and U. T has neighbors U and X. U has neighbors, where's U? U has neighbors S and T. V has U has S and X. W has neighbors S and X. Oh, no, I think I made a mistake. That's not supposed to happen. Sorry, I think I draw my thing wrong. I'm sorry, guys. This is not supposed to. No, it's okay. No, I'm right. No, it's correct. And then X has neighbors V, W, and T. V, W, and T. Just quickly calculating degrees. 3, 2, 2, 2, 2, and 3. Everything matches. Everything is so good. So I now know that the degree 3 on the left, there are B and C. They have to be sent to S or X. Which way, I don't know yet. But let's now list what I called the degree of the neighbors. So degree, I denoted this. The degree of the neighbors. So the degree of B. B has degree 3 and C has degree 3. Okay. A has degree 2, F has degree 2, and D has degree 2. I'm just reading it from my table. C, the neighbors of C are A, E, and D. A has degree, so right. So I'm now going here. So what are the degrees of these 3 guys? That's what I'm going to write here. Degree of A, I read that is 2. Degree of A is 2. Degree of D is 2. So 2, 2, 2. 2, 2, 2. B has degree 3 and C has degree 3. We already know that. C has degree 2. F has degree 2. And no. C has degree 3. Sorry, C has degree 3. F has degree 2. That's what it is. Sorry, let me do this again. Give me a sec. So C has degree 3. So many numbers I get confused, and 3 has degree 2. F has degree 2. Okay. E has degree 2, and B has degree 3. Okay, so what I see. That's that pattern. And what do we have here? Degree of n, the neighborhoods. W has degree, W has degree 2. V has degree 2, and U has degree 2. Okay. Then U has degree, so now the next second line, U has degree 2, X has degree 3, U has degree, U, what is, sorry, yeah, so here, I'm here now, degree of S, the degree of S is 3, degree of T is 2, S and X, that are neighbors of V. S has degree 3. S has degree 3. X has degree 3. Well, that's the same then, 3 and 3. And then V, W, N, what is that for a letter? T, I guess, yeah. V has degree 2. W has degree 2. And T has degree 2. Okay. Do the patterns matter? Do these patterns match? Sorry, I said it wrong. They are not the same, but look, each pattern, the 3-3 pattern, I actually have twice here, but I also have it exactly twice here. So not only do the patterns have to match, the number of times that the pattern, the number of times the pattern occurs must also be the same. It's again the graph invariant. So that matches. What about the 2 2s? 2 2 2 2 2 2 2 2 2 2, right? Those two also match. And then 3 2, that's a pattern 3 2, and there's also 3 2, rather 2 3. Doesn't matter how you pronounce it, how you order it. So again, they match. So okay, so I cannot rule that out either. Everything matches. When this starts happening, I start more and more believing that there is an isomorphism. And you can do this simultaneously. As you try to find out what happens, you can say, well, perhaps I can find an isomorphism. So now I'm going to start thinking about building an isomorphism. So sigma is going to go from vertices on the left to vertices on the right. And we know, let's think about what I'm going to do with A. Let's just think about A. I don't know why I should look at A, or should I look at another one first? It's a little bit guessing. And sometimes you might pick a choice and then you have to rethink your choice. Okay, A. Where am I going to send A to? Well, there are not that many combinations, possibilities, choices, right? Because not only have to send it to a degree 2, to one of those 4, but it actually have to have this pattern 3 3. So I can only send it to these 2 here. Which one? I'm going to pick one and hope that I pick the right one. I'm going to send A to V. Okay, so this is a guess. A guess, but it matches the degree of the neighborhoods. Let me write it that. Okay, make guess. I will once in a while have to make a guess, but it matches the degree of my. But it's a informed guess. So sometimes after I make a guess, other things are now fixed. And what is now fixed? Let's think about this. There's one thing I have no choice anymore, because there are 2 pattern 3 3s and 2 pattern 3 3s. I used one, I identified it with this one. Then there is no choice. This has to be identified by the other one. So this already fixes, so from there, so this is a D, has to be, go to, what was the other one? W. So if there is an isomorphism that sends A to V, then it must send D to W. Okay. Now, let's think what we have done. We sent A to V. Okay, so that means that the neighbors of A must be sent to, let's now look at neighborhood. So I'm going to do this a little bit, hopefully you can see. These are the neighbors of A, and I've sent A to V. So I'm using the same color here. So this tells me that B and C must be mapped to S or X. Okay, should I choose here? Well, they have the same degrees, so I have not really a choice here what to do. So I'm gonna wait a little bit, and yeah. I think I picked the not the I didn't make the smartest pick, but okay. I would like to do a do-over. Um, okay, let me do that over. Okay, so I can go on this way, and I think this is actually what the book does. But I want to show you that sometimes you can do a little bit easier thinking. So, okay, I'm not. I don't want to spend too much time anymore on this lecture. So I'm leaving this for the moment open, and I'm going to say, okay, that was one option, but just to show you that you can start from different options and it might or might not work. I am not showing that this works, but let's remember what I did. Okay, so let's take this away. So I'm not going to do this anymore. I'm just saying, okay, I'm going to try again. For some reason, I was not confident. Although nothing had happened yet. I could have gone on. But I'm thinking now more, I'm going to match. Let's try to match the 3-2 guys. That's the E. Let's see where E goes to. E. It has to go to one of the 3-2 guys. There are two of them here. That must be T or U. And again, I don't know which one. Don't say, oh, E is 3-2, so I should also take 3-2. No, because 3-2 and 2-3 are the same. And just show you, I'm going to pick T. Boldly, I pick T. So this is again a guess that matches the degrees of the neighbors. But once I've done this, we know now that there is one thing fixed now. The other 3-2, which is F on the left, has to be sent to the other 3-2 on the right. That was U. Okay, so let's mark this with our markers here. So we had E, we sent to T. Where was T? T. Okay. So now I know also that C and F, being the neighbors of E, must become U of X, U or X, because these are the neighbors of T. But look, I don't have that much choice anymore, right? Oh, I already said F has to go to U. That is already fixed here. F has to go to U. So in fact, so let me write this, do this, show this with a different color. So I'm gonna, each time that I match two, I give them the same color, right? So F is matching U. So when I'm talking about the neighbors of E here, I already know where this goes. So I know where this goes to the other neighbor of my corresponding T. So in other words, to X. C has to go to X because this is the only one of degree 3 neighbor. It has to go to the degree 3 neighbor. So we also have C goes to X. So also this is done. So let's mark this. Let's visualize this, that we see what we have done. C, right, has to go to X. Another thing is fixed. Do you see what else is now fixed? Because notice that there are always two of each kind, right? There are two of that have this pattern, there are two that this pattern, and two that pattern. And once I've chosen one on both sides, the other one is fixed. The other guy that has a 2-2 pattern, B, is now must be sent to the other guy that has a 2-2 pattern. So also fixed is. So I hope that you see what I'm trying to say here. Sometimes I make a guess, but sometimes I then make a deduction. That's what I try to indicate here. So I'm saying now B, being the only other one of the type 2-2-2 with neighbors of degree 2, 2, and 2 has to be sent, or the only one actually of degree 3. That's even easier to say. Has to be sent to S. So again, with my colors, I'll take it in no, green. I did already. What I can take, gray. So B. Ooh, no, it's this gray I need to go, guy. Oh, they come on. Gray. So B has to go to S. Okay. So only A and D have to be somehow matched, right? And how, I don't know yet. remember, this is actually what I was doing before. I was matching A with V, right? And then once I do that, I have no choice anymore. But let's think about A now. Oh no, the neighbors of A, I know, sorry, I know already what the neighbors of A are B and C. Oh, sorry, no, I didn't mean to color this. Oh, this one. The neighbors of A are B and C, and I know already what B and C become, as an X. So the neighbors, this, whatever send A to, sorry guys, I have to send A to V or to W, but I don't see how to distinguish them, so I'm going to make another guess. That's the guess that I originally made, but as I said, it was smarter if I did it the other way around. So A, and I guess that I have to send this to V, and then once I do this, I have no choice anymore. D, which is the other 3 guy, the only guy that has this pattern, also the only one left, has to be sent to W then. So just color coding everything. So we have here, let's do red. The A goes to V, okay, and then this line is some of them, and then finally my last one, blue, okay, blue. This blue. D goes to W. So I have found something that is compatible. And so with all the data I have, now this still does not mean that they're isomorphic. So how on earth do I check this now? And this is the last thing that I have to say, and this is, remember, we haven't talked about the matrices yet, and this is where it comes in. So follow me now. Okay, we need a little bit of space. No, I cannot. I'm gonna have to do this here. So I have a bit. There is now. I said E is mapped to T, but I should basically say it's both ways, right? F corresponds to U, C corresponds to X, B corresponds to S. What is? Sorry, guys. And so I can think either way. I can go from left to right or go from right to left. It doesn't matter anymore. Once I made a choice, I now have to say that they're compatible. So what I will do is the following. I'm going to make the adjacency matrix of G. Let's write down the adjacency matrix of G. How am I going to do this? Okay. The graphs, we don't really need the graphs anymore. We have all the data. So I'm going to actually get rid of the graphs. We can always get them back if we needed them, but we're going to do that. So I'm going to make the adjacency matrix. So remember that is A, B, C, D, E, and F. And then also A, B, C, D, E, and F. No, otherwise I cannot. I'm going to make mistakes, so I'm going to draw lines here. No, that's not normally part of the matrix. I'm making it more into a table, but after all, it's the same information. So how does this? I'm not going to make this for H yet, and you'll see why. So let's make this for A. Well, A will immediately from my thing you see B and C. So we have a 1 there and a 1 there, and everything is a 0. Of course, also there because there's no loop. Then A for B, it's A, F, and D. It's basically checking, right? It's if you want the check mark here, where we have the neighbors. So this is zeros. So you see, it's very easy to go from the adjacency list. This one, the adjacency list, to the adjacency matrix. They are the same data. It's just a different way of representing. C, A, E, and D. For D, it's B and C. For E, it's C and F. And for F, it's E and B. sanity check. Is this a symmetric matrix? In other words, if I flip it over here, is this symmetric? And you see, yes, it's symmetric. You see this corresponds to this element would map to there. If you would draw this very nicely in a nice grid, then you see much better symmetry. Okay? All right. Now, what is this adjacency matrix? Is the vertices and the edges. Now, an isomorphism has to preserve this edge relation, right? It preserves the edge relation. So wherever there was a 1 there, the corresponding 1 should also be a 1. Okay? So what I'm now trying to say, follow with me. I'm now going to make a matrix here. So this was for G, right? Here I'm not going to make G. I am calculating the matrix that it would be if I would rename the columns in the way that I suggested, namely that, for instance, A should go to V. So what I'm going to do, so follow this please. I'm going to use the same order that I have here, A, B, C, D, E, F, and then list here the images of A, B, C, D, E under my map. So A is mapped to V. So I put V here. B is mapped to S. So I'm going to put S here. C is mapped to the pink one, the purple one goes to X. I'm just going to, if you don't, you can also do it here on the list, right? I have it here. D, that was the blue one, goes to W. E, that was green, that goes to T. And F, that goes to U. So what I get here is incidence matrix, a listing of the vertices of N. Not perhaps the listing that we originally started with, but we get a listing because we have a map that did this. Now, at the other hand, I also, sorry, this is H, right? We're now working on H. If I want to make, I'm going to make now an adjacency matrix of for H using this order of the columns, but then I have to use the same order for the rows. So this is also has to be V, S, X, W, T, U. Meaning that A is mapped to V, B is mapped to S, and again, this tells me the isomorphism, right? I'm implementing the isomorphism. But now you say, okay, so they copy 0 to there and copy 1 to there. No. That's not what I'm going to copy. What I'm now going to do is use my H to calculate the incidence matrix of H. So the information I have here. So let's do that. So V, let's start with V. V has neighbors S and X. So S and X. All the rest is going to be zeros. Now what am I looking for? This isomorphism has to map this adjacency matrix of G to the adjacency matrix of H. In other words, it has to be the same matrix, column by column, row by row. So let's look. The first column is the same. The first row is already the same. That's very promising. Doesn't mean yet I'm gone right, but it means I seem to be on the right way. So now B, what is B? B has neighbors A. No, not B. Sorry, that we know B already. S neighbors W, V, and U. W is here, V is there, and U is there. I have to mark them in this order that I was given, right? And the rest is zeros. Does this correspond? Yes. That's good news, right? Okay. X has neighbors V, W, and T. I'm reading this here, right? X has neighbors V, W, and T. So X has neighbors V, W, and T. V, W, and T, and that's 0, 0, 0 otherwise. Notice that I'm still getting the same row because we have the third row now, so it's not aligned, but it is the third row. So this is still the same as that. Very promising. We keep going. W, the neighbors of W are S and X. S is here and X is there, so this is 0, 0, 0, 0. The neighbors of T are U and X. U is here, X is here. I always have to keep looking for them now because they are listed in different order, right? And then finally U, S and T, 0, 0, 0, 0. And lo and behold, this matrix is the same as this matrix. They are the same matrices, and that proves that we have an isomorphism. I think, guys, that I have to stop. I'm gonna give you some homework. Sorry about that. And then I'm also we will do a quiz on this, and you'll see the hardest part is that there are two possibilities. Namely, it's not isomorphic, and then you have to find something that tells them apart, like in this example that we had here, or they're isomorphic, and then you have to give an isomorphism. It's a totally different strategy, although it is still very much same kind of investigation that you need to do. The neighbors, the degrees of the neighbors, and then you start making the isomorphism if there is one, or you say, okay, that there's no possible match. Now you might say, Professor, that's very difficult, but that seems to be very complicated. Can we not do this easier? No. And that's actually a very open, a big problem still in graph theories, that we don't know yet how to check that two graphs are invariant, are isomorphic in an efficient way. There are algorithms that are exponential, but at the moment we do not have a polynomial, and that makes it a very difficult problem to check that two graphs are isomorphic. And this is useful in applications. I don't discuss the applications. There are applications in chemistry on molecular bonds. They can be represented by graphs. And so you have a molecule that can be the bonds between the various components would give you a graph. But you could have a molecule that has different different organization, but it might be therefore the same molecule. And these are very complex molecules, and so, particularly if one wants to list all the molecules that are available, if we're looking for a new usage of these molecules. I'm not a chemist, I'm a biologist, so I have no idea what they all do for. But if you construct in a lab a molecule, is this the same molecule that somebody else already had constructed? And that is, you can do this by checking that the graphs are isomorphic or not. So that's why it's an important problem, and it's not an easy problem, so there is no shortcut here. Okay, so let's look at the homeworks. We'll give you homework, and we go over them, and then we'll do a quiz on this as well.